Hello. So this is the final video of section 2.1, um, and so we're going to start off. We ended last video by going over um, some warnings about matrix multiplication, kind of like a list of here's what you can't always do. We're going to start this video by going over things that you can always do with matrix multiplication. Most of them, again, these are properties that should look similar, especially sort of given the trend of this course. I don't want to spend too much time on them, except one of these, because I want to introduce a new matrix, which will pop up quite frequently. It should look somewhat familiar at this point. We just haven't defined it in this way. And then we're going to learn a few new things. Yeah, the book really packs a lot into this section. So we'll just jump right in. Like I said, I think properties 1 through 4 are all fairly straightforward. I haven't written out 5 yet for good reason, but so this is the distributive property that says if I can multiply A, B, and C, then it doesn't really matter which order I do the multiplication in as long as I don't flip it around, right? So like this order has to stay the same. But I could do B times C and then multiply that by N on the left, or I could do A times B and then multiply that by C. These two properties are the same, just sort of what side of B and C I'm multiplying A on. And remember, that does matter, because remember the rule we learned for when we can multiply matrices. If you'll remember, the number of columns of the matrix on the left should equal the number of rows of the matrix on the right. Right, so for example, in this product, the number of columns of A would have to equal the number of rows of B. And so in this way, the order or the side on which I'm multiplying A really does matter. And remember, that was like one of the big warnings, and one of the really big interesting things about matrix multiplication in general is that it is not commutative. And this is one of the unique things that we've learned, I think, in this point in our, in math, really, that like, everything is just commutative. It doesn't matter what order I do it in. But with matrix multiplication, order does matter quite a bit because sometimes, switching the order can turn what was a valid product into something that's not valid. So that's 2 and 3. 4 says here if R is a scalar and I've got R times this product AB, it doesn't really matter where R lives in the product. I can multiply R by one of the matrices first, or I can factor out a scalar, do the multiplication, and then factor the scalar back in. All right, so property 5. I'm going to start with a new definition. So the M by M identity matrix, which we will often denote as I sub M. So this is a special matrix. It is square M by M. It's a diagonal matrix with only 1s on the diagonal. So this matrix here. Or this would be the 3 by 3 identity matrix. You might recognize it because it should look an awful lot like a reduced row echelon form matrix that corresponds to a 1-to-1 linear transformation, or a system of equations. This could correspond to 3 equations for which the matrix equation AX equals B always has a solution. But it's also known as the identity matrix. Why is that? Well, because if I were to take any matrix that was I have to get my dimensions right here. If I were to take any matrix that had m columns, so if A was a n by m matrix, or if A was an m by n matrix. So we'll maybe do an example with, say, we did that, and let's say we had this matrix. So here A is a 3 by 2 matrix. And so notice this product is valid. What happens when I multiply a matrix in a valid way by the corresponding identity matrix? Well, let's do our matrix multiplication dance. 1, 0, 0, matches up with 1, 2, 3. 1, 0, 0 matches up with 4, 5, 6. 0, 1, 0 matches up with 1, 2, 3. 0, 1, 0 matches up with 4, 5, 6. And 0, 0, 1. Well, you might get the trend at this point. It turns out the identity matrix, when multiplied by any matrix in a valid way, just returns that same matrix. And so that's why we call it the identity. And so if A is an m by n matrix, then I sub m times A is equal to A, and A times I sub n is equal to A. And so notice here, I'm choosing the correct identity matrix based on the dimensions of A. And this sort of corresponds, I think we had talked about something called the multiplicative identity when we were talking about vectors. This is sort of that corresponding idea. It's the object that we have, this object now we're thinking of matrices, that under multiplication, when I multiply it by something, doesn't inherently change that thing. So we'll talk a lot more about this type of a matrix later on. But moving on from this, I want to introduce sort of two new ideas that the end of this section introduces. And we're going to do some more matrix multiplication. All right, so the first thing we want to introduce are what we call powers of a matrix. And again, this is one of those things that I think ends up being defined sort of how you would want it to be defined. Important to note here that this only makes sense with square matrices. So if A is an n by n matrix, right, so it has to have the same number of columns and rows, then we say that A to the k, where here k is a number. And I'm specifying here that k is a number because we're going to introduce something where we really get to see some of the limitations of notation of math in a second. But here k is a number. And so if A is an n by n matrix, then A to the k is just equal to A times itself, k times. And so it's defined exactly how powers are defined, basically exactly how powers are defined normally, just with regular numbers, except here we're just doing it with matrices. And I do believe it is the convention, I think partly because of how this process, or how this operation works with numbers as well, that A to the 0 is just equal to the identity matrix I sub n. So A to the 1 would just be A to the 2 would be A times A to the 3 would be A times A times A. And notice that, again, we have to specify A as a square matrix that has the same number of columns and rows, because otherwise this product would not make sense. So we'll do one example just to see how this works. I think I'm going to use this matrix again in a second, so I'll sort of box it off there. Let's say A was equal to the matrix 1, 2, 3, 0, 4, 0, negative 1, negative 2, negative 3. So then A squared equals A times A. Example. And so this is, again, 1, 2, 3, 0, 4, 0, negative 1, negative 2, negative 3. All right, so we'll do the matrix multiplication dance. Maybe I'll do the first row going across, and then I'll just start to fill it in. So first row, 1, 2, 3 matches up with 1, 0, negative 1 to give me negative 2. 1, 2, 3 matches up with 2, 4, negative 2 to give me 4. All right, we'll double check that. So 2 plus 8 minus 6 is equal to 4. And then finally, 1, 2, 3 matches up with 3, negative 3 to give me 3 minus 9, or negative 6. All right, so continuing this, 0, 4, 0 matches up with 1, 0, negative 1 to actually give me 0. 0, 4, 0 matches up with 2, 4, negative 2 to give me 16. 0, 4, 0 matches up with this to give me 0. And then I'll fill in the last row a little quicker here. This you can actually sort of get the solution because you might notice that this row is equal to negative 1 times this row. So that's where you get that from. All right, so powers of a matrix. A fairly sensible thing, but important to sort of introduce this notation. And when you see a to the 2 or a to the 3, that's what it is talking about. All right, it's also very odd that the book, well, maybe it's not super odd. Now we're going to learn what is called the transpose of a matrix. And this is not to be confused with powers of a matrix. So, if A is an M by N matrix, then the transpose of A which we denote by A superscript T. And so this is where I do apologize for math's choosing of this notation. If you see A superscript T, this is always, always, always asking for the transpose. So I think it's very tempting because this looks like A to a power. To want to think that this is A to some power, this is A transpose, which as we'll see is very different from A to a power. So A superscript T is the transpose, denoted A superscript T, is the N by M matrix whose rows equal the columns of A. So it is basically, if you think about it, you're sort of taking a mirror and reflecting A like around this way. And that's a really poor way of thinking about it. I just like to, if I'm asked to find the transpose, I just like to read across the rows of A and fill in A transpose using the columns. So we'll give a couple examples here using these two matrices, A and B, which I'll fill in right now. Very original. 1, 2, 3, 4, 5, 6. All right, so A transpose. How do we find it? So it's going to be a 3 by 3 matrix because A is a 3 by 3 matrix, right? So if we swap the indices, it's still 3 by 3. I'm going to fill down the rows of A transpose while going across, down the columns, of A transpose while going across the rows of A. So first column would be 1, 2, 3. Second column would be 0, 4, 0. And the third column would be negative 1, negative 2, negative 3. So it's sort of there you go. It's the reflection across the diagonal entries, right? So if you imagine reflecting everything around the diagonal entries of A, you'd get A transpose. Notice in particular because the diagonal entries are fixed, right? So the diagonal entries of A and its transpose are the same. And so now B transpose, well, B is a 3 by 2 matrix. So B transpose will be a 2 by 3 matrix. And again, we're going to read across and go down. So 1, 4, 2, 5, 3, 6. All right. I almost asked for questions again. So certainly if there are any questions about that, email me. This is a very odd thing. But It's one of those things. So this is one of those definitions, I'll say it right now, that we kind of define. It's very important because we are going to talk about it. It'll pop up a lot. But like we define it now, and then we kind of don't use it for a while. But it's definitely a definition. It's absolutely a definition you have to learn, and it is like it's wonderful for us math teachers because it's just like a great question to put on the test to say like calculate this product, and it's A transpose times B. So I guess I'm sort of admitting math teacher tricks here, but make sure that like you have on some sticky note or something like A transpose is this, because it'll be one of those things that kind of lays low for a while, but then we'll bring back up again later. And so it's important to be comfortable with it. So much like everything we've introduced, the transpose has some nice properties that I want to talk about. I will give an example of one of them because I think most of them are pretty straightforward. But I'll give an example of one just so we can see why this is the case. All right, so we'll end with some properties. One, so notice, let's say I wanted to do the transpose twice, right? So let's say I wanted to take the transpose of B transpose. Well, B transpose is a 2 by 3 matrix. So B transpose is going to be a 3 by 2 matrix. And, well, first column is going to be 1, 2, 3. Second column is going to be 4, 5, 6. And so from this example here, the transpose of any matrix is just equal to the original matrix. That is, if you apply the transpose twice, you get back to where you started. So A transpose transpose is equal to A. We can distribute the transpose across sums. So A plus B quantity transpose is equal to A transpose plus B transpose. That one I think is fairly straightforward. Transposes don't care about scalars, so if I have a scalar R, then R times A quantity transpose, I can just factor out the scalar. Again, I think that one's fairly sensible. Like, switching the numbers around, it doesn't really, like, if they're all divisible by the same thing, I could just pull that thing out, switch it in, and bring the scalar back. Now, the very weird one, which I want to talk about here, what if we have A times B quantity transpose? What is that equal to? Well, actually, I'll just give it, and then we'll calculate it. So if I want to take the transpose of AB, this is actually equal to B transpose times A transpose. I'll circle that one because it's by far the weirdest. So if you want to distribute the transpose through a product, what you have to do is flip the product around and take each of the individual transposes. So I want to end on an example where we calculate A times B, and then we calculate B transpose times A transpose. All right, so the way I've left myself room here isn't great, so I'm going to sort of erase things a little sequentially here so I can give myself more room. But we're going to be working with the same matrices that I have had on the board. So A times B is equal to all right, so this is lining up the product. If we do the matrix dance a few times, I get the following matrix, 14, 8, negative 14, 32, 20, negative 32. All right. Now B transpose times A transpose, well, is equal to 1, 2, 3, 4, 5, 6 times 1, 2, 3, 0, 4, 0, negative 1, negative 2, negative 3. And so if you sort of imagine what's happening here, like if you look at how these products are working, like to get some intuitive idea as to why this is true, if you like the rows that were getting matched up are now going to sort of get matched up in the same way, but kind of in a different order, right? So notice here, this is going to be a 2 by 3 matrix. And, 1, 2, 3 matched up with 1, 2, 3. Well, that gives me 14. 1, 2, 3 matched up with 0, 4, 0 gives me 8. And 1, 2, 3 matched up negatively gives me negative 14. And then we could continue this either by doing the product or by looking at the matrix above. And you might notice, in fact, that these two matrices that we calculated here are, in fact, transposes of each other. And so, in fact, A times B transpose is equal to B transpose times A transpose. And, it helps me to remember this just sort of based on the order that the rows, when you're doing the dance, the order that the rows and columns get matched up in our multiplication process. So that's the transpose. Like I said, keep a note somewhere just sort of reminding you what the transpose is, because it'll pop up somewhat randomly, here and there. And it's like never something we focus on like a whole lot. And so I think, it was definitely one of those things for me that like I learned, I was like, oh yeah, that makes sense. And then, a month went by, I forgot it, and all of a sudden a transpose question pops up. And it's like, oh yeah, what's that? So anyways, that is the end of this section. I think this should end week 2. And so next week we will pick back up in chapter 2 with section 2.2.